Welcome to the heron's still water. Look closely at the shallows and see Wren, our blue heron, stalking her morning catch. If we try to measure the depth of this pool using only whole meters, we run into a problem. The water here is shallow, far less than a full meter deep. To understand exactly where to step, Wren needs precise increments, tenths, hundredths, and even thousandths of a meter. She reads the water by carefully dipping her bill beneath the surface, finding the exact depth of the still pool. Watch this panel here on the screen. As Wren tests the water, a painted depth strip fills with color beside her leg. We read this measurement as 3/10ths of a meter. Now, suppose she moves between two different pools. One measures 0.45 meters deep, and the other measures 0.50. A quick glance might make you think the number with more digits is the larger amount. But treating decimals like whole numbers will lead you straight into the mud. To read these depths accurately, we have to entirely abandon the instinct to count how long a number is, and rely instead on the positional hierarchy of the digits. To see exactly how this works, Wren steps toward a new section of the pond to compare those two measurements side by side. Here is the fundamental rule for comparing decimals. First, we stack the measurements and perfectly line up the decimal points. Then we evaluate the highest place value first, moving left to right. That brings us immediately to the tenths column, sitting directly right of the decimal point. The top pool has 4/10ths. The bottom pool has 5. Since 5 beats 4, the bottom pool is definitively deeper. The comparison is one right there at the top of the hierarchy. Even if the top number had a long string of digits trailing after the 4, it wouldn't change a thing. The tenths place settles the contest. To see exactly why those leftmost digits carry so much power, look at this leaf panel showing a new measurement, 0.305. The 3 sits in the tenths position. That represents 3 sets of 1/10th of a meter. Moving right, the 0 in the hundredths position functions strictly as a placeholder. It keeps the structure intact, but it adds absolutely 0 value to the depth. Finally, the 5 represents 5 sets of 1/1000th. A thousandth is a fractionally tiny drop of water compared to a tenth. When we read this entire string, we don't call out isolated digits. We read it as one cohesive value, 305 thousandths. Expanding the decimal visualizes the mathematical weight of each position. It proves why fair comparisons must start from the largest place value on the left. So what happens if we take a decimal and add zeros to the end? Does turning 0.5 into 0.500 change its actual physical amount? Look at this painted depth strip. It represents a baseline of exactly 5/10ths of a meter. If we slice those tenths into 10 smaller pieces each, we create 50 hundredths. The label updates to 0.50, but the overall height of the water remains identical. Slice it again into microscopic increments, and we have 500 thousandths. The label changes to 0.500, yet the volume remains completely static. Trailing zeros merely rename the decimal into finer cuts for easier alignment. This debunks the illusion that adding digits to the end increases a number's value. Now, trusting this protocol, Wren makes her choice. She steps into the deepest pool and stills her body. The math validates her physical choice. The winning measurement glows. 0.50 outpaces 0.45. It all comes back to a core operating mantra. Line up the points, compare the biggest place first. Remember, line up the points, the deepest water always wins. I will see you at the next bend. By unlearning the bias that longer means bigger and trusting the positional hierarchy instead, you possess the foolproof logic required to accurately decode measurement, money, and all future decimal operations.